If you have a multivariable function, then when we call the critical points of your function are the places where the gradient of your function is the 0 vector. And so whenever I say the gradient equals 0 here, what I mean is that it's actually the vector that has all zeros as entries, right? So remember, the gradient of your function is the vector where all of the entries are the partial derivatives of that function. So if your function is a function of 7 variables, then the gradient vector has 7 entries for the 7 partial derivatives. And if I say gradient equals 0, I just mean that's going to be a vector with 7 zeros as its entries. So if your multivariable function is continuously differentiable, meaning you can take all 7 partial derivatives and all of those partial derivatives are continuous functions, we call it smooth. And if f is smooth, then any sort of relative maximum or relative minimum has to be located at a critical point. At a critical point, like suppose that you found a critical point of your function, a critical point might be a relative maximum, it might be a relative minimum, it might be what we call a saddle point, and it might be none of those. It might just be a critical point that happens to be nothing at all. If you want to figure out the difference between those cases, what you're going to do is you're going to take the determinant of what we call the Hessian matrix. If the determinant of the Hessian matrix is a positive real number greater than 0, I wrote like the second partial derivative with respect to x, but you could also do the second partial derivative with respect to y. But if you look at the second partial derivatives and they are negative, then you're looking at a relative maximum. If the determinant of the Hessian matrix is greater than 0 and the second partial derivatives are greater than 0, then your function has a relative minimum. If the determinant is less than 0, then you've got a saddle point. And if the determinant of the Hessian is equal to 0, then we say this test is inconclusive. And that means it could be a relative maximum, it could be a relative minimum, it could be a saddle point, or it could be none of those things. We have absolutely no new information about what that critical point is if the determinant is 0. Okay, so if you have a single variable function, then what this looks like is, well, the gradient of a single variable function would just be a vector with one entry, right? And that entry would be the partial of f with respect to x. But in the case of a single variable function, the partial derivative is the total derivative. There's nothing else going on in terms of independent variables, and so that's just the derivative. And so whenever I say the critical point is the gradient equal to the 0 vector, that's the same thing as saying the first derivative of a single variable function is equal to 0. And that's consistent with your definition of a critical point that you learned in Calculus 1. So for a single variable function, the Hessian matrix would be a 1-by-1 matrix, and the only entry in that 1-by-1 matrix would be the second derivative of f with respect to x. And so this test, and by the way, the determinant would be the same thing. The determinant of a 1-by-1 matrix is just the only entry in the 1-by-1 matrix. So what this test would be saying is that if your second derivative is greater than 0, then you have a situation where it's concave down, so that means you have a relative minimum. right? So that would sort of correspond to this situation. If your second derivative is less than 0, then we're talking about a case where it's oh, sorry, this was concave up, and so then this is concave down, and then it's a relative maximum. I think I misspoke a second ago. I wrote the right thing, I just said the wrong thing. We don't have saddle points for a single variable function. A saddle point is whenever you have a relative minimum. If you look at one trace, and then if you look at a different trace, it appears to have a relative maximum. And so for a single variable function, we don't have different traces, and so we're not going to have saddle points for single variable functions. But we can still have a case where this is inconclusive for a single variable function. If your second derivative is equal to 0, then it's inconclusive, which means you might have a relative minimum, you might have a relative maximum, and you might have neither. You can have a critical point where it's not a relative minimum or a maximum. I think I showed you guys this before spring break, but I'm going to show you again just because I think it's useful. In the case of a single variable function, right, this would be a case where it's concave up, so the second derivative is positive, and so we expect to have a relative minimum. And sure enough, at this one critical point of the function, where the derivative is equal to 0, that's a relative minimum at the critical point. Likewise, if I just make that negative, the second derivative is negative, so it's concave down, so you have a relative maximum at the critical point. If you had, however, something like this, this is a case where the second derivative is 0, and so you have a critical point here, but it's not a relative minimum and it's not a relative maximum, right? This is a critical point where the derivative is 0, but since the second derivative is 0, you don't have a relative minimum or a maximum. But just because the second derivative is 0 doesn't mean you have this case, right? Because if I have this function, x to the 4th, now that's a relative minimum, but the second derivative is 0. And so that's why we say the test is inconclusive if the second derivative is 0, because it might be concave up, it might be concave down, it might be neither, right? So if the second derivative is 0, we have no idea what's going on. We don't know if it's minimum, maximum, or neither. Okay, so then the additional case that gets added whenever we have a multivariable function is something like this. We call it a saddle point because if I look at this trace, that trace appears to be concave up, so it looks like I have a relative minimum there at the origin. But then if I turn my view, now it looks like it's concave down, and it looks like I have a relative maximum. So that point there is a critical point, where the derivative in every direction is 0, and yet it's neither a relative maximum nor a relative minimum. We call that a saddle point. With multivariable functions, you can still have cases where it's not a minimum, it's not a maximum, and it's not a saddle point. Like I think this works. Yeah. So this surface right here, at the origin, it's not a saddle point, it's not a minimum, it's not a maximum, it's neither. It's none of the above. And so that's a possibility as well with multivariable functions. So if f is a function of two variables, like f of x and y, then the gradient of f is going to be a vector with two entries, partial f with respect to x, partial f with respect to y. Oops, y, not f. And the critical points are where this vector is equal to the 0 vector with two entries, right? So I need both partial derivatives to be equal to 0 at a critical point. And the Hessian matrix of this function of two variables would be a matrix where the top left entry is the second partial derivative with respect to x. The bottom right entry is the second partial derivative with respect to y. And then the off-diagonal entries of this Hessian matrix are going to be the mixed partial derivatives. And I think in this class we're always going to talk about smooth functions, which means that these partial derivatives are continuous functions, which means that these mixed partials are actually the same thing, and it doesn't matter which order you take the partial derivatives in. And so if I talk about the determinant of this Hessian matrix, and sometimes we use like the absolute value symbols to talk about the determinant, but the determinant is going to be the second partial with respect to x times the second partial with respect to y minus the mixed partial derivative squared. So you first find the place where the gradient is equal to 0. Those are your critical points. And then you calculate the determinant of this Hessian matrix. And the determinant of the Hessian matrix always looks like this for functions of two variables. And using the determinant of the Hessian matrix, I'm not going to copy all of this down again, but you can use that to differentiate between the cases of a relative maximum, relative minimum, a saddle point, and if your determinant happens to be 0, then you can't tell any new information about your function or what that is at that critical point. Could be anything. Okay. So far, so good. So hopefully we have time for an example before we go. So I'm going to say that g is a function of two variables. Ooh, okay. And I want to find the critical points. So of course the critical points are the places where the gradient of g is equal to 0. And the gradient of g equals to 0 means that the partial of g with respect to x has to be 0, and the partial of g with respect to y has to be 0. The partial of g with respect to x would be 2x minus 1, and the partial of g with respect to y would be minus 2y minus 1. And that means the x-coordinate has to be 1/2, and the y-coordinate has to be negative 1/2. So I know that I have a critical point of this function at the coordinate pair 1/2 comma negative 1/2. I don't know yet whether this critical point is going to be a maximum or a minimum or a saddle point. So one thing I'm going to try is just to take that determinant of the Hessian matrix. And the determinant of my Hessian matrix for a 2x2 Hessian matrix like this is going to be fxx, fyy, minus fxy squared.
Can we just say like are we allowed to just say that the function is smoothly continuous? Smoothly differentiable or
Continuously differentiable? Mm-hmm.
Are you allowed just to state it and then do the calculation?
You don't even have to state it.
Okay.
Yeah, you don't even have to worry about that. In this function, and I'm pretty sure in all the other functions that the book gives you for homework, I think that they are all continuously differentiable. So, yeah, just assume that and don't worry about that in this class. So that means I have to take these second partial derivatives, though, to figure out what's going on. And so my function was actually named g and not f, so I could just change those to g's. But g xx would be 2. g yy would be -2. And then g xy would be what? Zero. Yep. So this was the partial with respect to x. It was 2x minus 1. If I took the partial derivative of this with respect to y, then it would just be 0, right? Or, alternatively, this was the partial with respect to y. And if I took the partial with respect to x of this expression, it would also be 0. Okay. So then, the determinant of my Hessian matrix is equal to 2 times -2, which is -4, minus 0 squared. So if this determinant is negative, that means my critical point is a what? A saddle point. Yeah. Graph this really quick and then we'll call it a day. So if I do z equals x squared minus y squared minus x minus y, then the critical point we found was half negative half. And so, did I type in everything right? This looks like it's off by a little bit.
Minus
C, yeah.
Instead of minus x.
That's in the way. Oh yeah, okay. Ah, there it goes. Okay, so right now it's smack dab where it should be at the saddle point. Okay.